There we go. It was cold outside. But it was one of those, they have to get it in before the end of the month, and there's only so many days left.
Do we really do it every month?
We have to do there's a safety drill every month.
Oh, okay.
Whether it's fire, lockdown, tornado, earthquake, whatever it is. We've done one of those in a long time.
I don't get to move to California.
We did. They just didn't make it be a super intense one where we had to sit by the walls because trauma. That's just where we pull the door, pull the curtain, keep going, and they come and jiggle that door handle.
If someone's in here, I'm not.
No, no. Oop.
I expect you to pull out your wand and suggestions.
Oh, I've got wasp spray in my cabinet. Yes, because that is essentially mace with a 30-foot range. But it is not technically a weapon, so I have wasp spray that I keep right there. And that's part of the reason we have loose chairs, is then you can jam the door shut. There's plans. Has been all thought and planned out. Hopefully never is used. All right. So we're going to start with our exponential functions. We're mostly going to be starting with our a times b to the x, and just working with that. I put the h and the k in here because we'll use them eventually, but I don't think we're going to get all the way to most of them today. But a, h, and k have the same jobs they've normally had. A will do our vertical stretch or compress. It'll do our vertical reflection over the x-axis. Most of the time, it's also our y-intercept on exponential functions. B is our base. It is not a transformation. B is the starting place. It is our growth factor. It's how much something is growing by. It may involve a rate. It may involve a multiplier. There's lots of ways we can word it. But our base, our B, has to be a positive number. We cannot have a negative base. Absolutely cannot. That would be something that switches between being positive and negative depending on whether our exponent was positive or negative. And it's super gross. So we're not doing anything with negative bases, at all. Our x's in our exponents, when we're looking at story problems, those are going to be a unit of time. So sometimes we're going to have to be really careful with what the unit is. And if we have an asymptote, if there's a number at the end, that's what our k is. It's our vertical shift, so it would just move our function up or down. And it affects our domain and range. Again, we're not going to get super duper into those, but I just was putting them up here so we had all the pieces for when we get to them. I like to give us one of those quick one-stop shop to find all the pieces. This is our one-stop shop for all the pieces page. Because what we're going to start with is just by looking at our a times b to the x. I'm going to give us a very basic story problem. We're going to write an equation. And we're going to make an estimate on what's going to happen. So, I'm going to change it in 3, 2, 1. Just give you more. So, we've got fruit flies. That is a very common type of problem we're going to see for exponential functions. If the number of fruit flies triples every 4 hours, and we currently have 100 fruit flies. That's the context of our situation we're going to work with here. And we're going to write an equation using our most basic of basic forms with our a times b to the x. Those are the pieces we're going to look at here. I know. Luckily, we go through these parts really fast, but then we get into logs. So I know. This next 2 weeks, we have exponentials and logs. Oh yes.
We're gonna have to learn how to do those without calculators too, right?
No, we have
We
calculators.
get calculators.
Yeah, but I mean, I don't know.
We're gonna have little bits, not anything decimally without calculators. Literally, that's not a thing. Even back in the day, they did pre-calculator. That's what a slide rule is for. No. Or you need a book with a reference table for logs of other bases. No. We have calculators. We just have to know how to use them. Okay, but we're not there yet. Let's talk about the exponentials first. Don't stop scaring yourself. So, A is going to be our starting amount. A is where we begin. So this is always going to be our starting amount. So how many do we start with? 100. So A is 100. Our base is how much it's growing by. Our number of flies are going to triple. So our base is going to be 3 because it multiplies by 3 every chunk of time. So we have to be careful because it's not that it's tripling every hour. It's tripling every 4 hours. So if I want to be able to say at 1 hour I have this many flies, at 12 hours I have this many flies, at 24 hours I have this many flies, I want to be able to put in hours at the top. So we've got to think about how we could write that as our exponent. So if I have 4 hours, how many times is it going to triple? If the amount of flies triples. Once. If I have 4 hours, it triples 1 time because it triples every 4 hours. So at 8 hours, how many times does it triple? Twice. At 12 hours, how many times does it triple? What are we doing with that number of hours I'm giving you? Dividing it by 4. So if we have some number of hours, x, to get the amount of flies we have, we need to divide it by 4. That's why I worded it the way I did. Because we have a weird unit of time, I have to divide my number of hours. That's all it is. If you choose to go the route of, well, I'd rather just think of it in how many chunks of 4 hours that is, that's totally fine. But this makes it easier. Because then we're going to look to estimate how many flies there's going to be in 24 hours. And the way we set this up, we just know that this guy's our x. So we substitute my 24. That's x.
So it's always x over the number it gives you?
If we have a weird unit of time, it's going to be x over the weird unit of time.
If you so like if you had only 1 hour, if you were trying to like solve this
Mhm.
and like solve x, but it's only like 1 hour, would it then like the 4 be like the root?
Yes,
Like
it is technically, it would make that be a 4th root.
Okay.
But we can also just simplify it. And since we're able to use calculators, we're going to do 3 to the power of, you can either put 1/4 or you can put 0.25. And it'll do the same thing. The calculators will do that. So what we're going to do is we're going to substitute this in. We're going to have our 100 times 3 to the power of 24 over 4. And we could type it in just like that. The calculators can do it. It's a little annoying and we have to be super careful. Or we can simplify that. What is 24 divided by 4?
6.
So we have 100 times 3 to the 6th.
72,900. Fruit flies, that's disgusting.
I know. That is why you got to catch them when there's not that many. And not let them stay in your house because they multiply really fast.
How do we multiply with food? Do they just like...
With each other?
They like
Oh.
call, they like call their besties.
They call their besties and then they have a party.
Oh.
Which is why fruit flies are used a lot in science experiments, is because you can get a lot of generations in the span of a couple of weeks. So you can do generational studies over the span of a month instead of having to wait for humans for that to be, you know, centuries to get several generations. That's why they use fruit flies a lot in science experiments, is just because their life cycle is so fast.
Not eating fruit is not the...
Not eating fruit is not the solution to not getting fruit flies.
This is not gonna happen.
They're called fruit flies, but they eat a lot of things. It's just about keeping tidy. It's literal trash. Okay. So we're not going to have a ton of questions where we have, you know, fruit fly-based problems, things like that. Just kind of getting us back into the vibe of thinking about these things with exponential functions. I'm going to give us another kind of rundown of when we talk about growth versus decay, because those are our vocab words here. Yes. We're going to talk when we can tell exponential growth versus exponential decay. Because there's a couple of special things about growth and a couple of special things about decay. Exponential growth is always increasing. Every single time it will be increasing. Which means it is a one-to-one function. That was one of our things that we used to define a one-to-one function, is that it was always increasing. Exponential growth happens, I'm going to start with when A is positive, and our base, our B, has to be greater than 1. So my A has to be positive and my base is greater than 1 for it to be exponential growth. If I have my A being positive and my B being greater than 1, it's going to look kind of like this. We've seen these before. We've worked with them. Tying in some of the pieces from that first page of a gabillion pieces of information. This point right here, that's going to be our A, our y-intercept for the most part. If I scooch over to where x equals 1, we're going to get the next point being A times B. We are always going to have a horizontal asymptote on these. And it's going to be at K.
Then the horizontal asymptote.
Always, every single time. So if there's anything added to the end of our equation that just gives us a vertical or a horizontal shift, and that just shows where that asymptote is. And then the last piece that doesn't come up super often, but I'm just going to put it here in case we see it later, is where we start with our A and then our A times B. If we have any horizontal shift, that's the piece that moves. It moves my A either left or right from that y-intercept place. So that's why I say it's most often our y-intercept. So H would be where our A value is. H plus 1 would be where A times B is. And that's how we're going to get graphs for these and sketch them out. You can always make full tables, but honestly, these are way faster to do this way. And so we'll go through, when we get to graphing, we'll go through it. I promise. I'm just giving you kind of, again, one of those pages. So if we're looking at stuff, trying to figure out where things are, that's what they are. Going to give the same kind of list for our exponential decay. So exponential decay, instead of being always increasing, it's always decreasing. And again, we're going to look at when our A values are positive and what that means for our B. And see what happens when A changes things. So when our A value is positive, and our B, which always has to be bigger than 0. Remember, we can't do negative numbers. We wind up with something that's like switching signs like this, and it gets really, really crazy. But it also has to be then less than 1. So my base is going to be fractions. It's going to be small. 1/3, 1/2, 7/8, 1/200. They're going to be small. And it's decaying. What that would look like on a graph, just giving us another little basic sketch, that it would be falling like this. And it may be steeper, it may be shallower, but it's just falling. It's always decreasing. And it has all those same pieces where we're still going to have our asymptote, our horizontal asymptote at the K, what should be the y-intercept most of the times is going to be where we have A, our starting amount. If I go over to where x is 1, it's going to be a times b, which we'll look at these a lot closer when we get into the graphing stuff, which we will get to, just not today. Just want to give us one of those, we can see all the pieces things. And then if we have any horizontal shifts, it just moves where our a is. So this would be where we have an h. We are not going to have h very often, but just so we can see it, if it's there, that's where we would get that. We only talk about our exponential growth when a is positive. Same thing with our decay. Use my ultra super duper high tech image for us to be able to see what happens when we have a reflecting. So if I have an exponential growth, so my b is bigger than 1 and we have an a that's positive, but then I reflect it over the x-axis because my a is negative. Is it still going to be growth? No, because this is now falling. So if my a is negative and my b is bigger than 1, I actually get decay. If I have decay and my b is a fraction and I reflect it over the x-axis, is it still decay? No, it's starting really low and it's getting higher. It's not continuing up to infinity, but it is still growing. Just little bits at a time. So if your a is negative, your b rules switch. That's why I didn't write it down.
Is a times b always at 1 for x?
It'll be 1 away from if we have a horizontal shift.
Okay.
Most of the time, yes. I'd say 95% of the time, yes. And when we get to the graphing, I will walk us through that, but it's just one of those again. I like to give us one of those, I forget where to do this and look at one place and find it without having to flip the billion pages to get there. So we're going to start by identifying whether or not it is growth or decay. And I knew we had that bio comment, so I'm trying to save us some time, so I actually printed them out, the little equations we're going to look at, because literally all we need to know is it growth or is it decay? And it would take us longer to write them down than to think it through if I have them printed out for you. So I have the equations we're going to look at. They're in the right order. We don't need to cut them apart. You don't need more space in this, because all we're going to say is it growth or is it decay? Just trying to make it so we can get through things as quickly as possible. Alright, so what we're going to do with this first set of questions is we're just going to say, is it growth or is it decay?
I never put my clothes back on anymore.
So, same questions, same order. I just gave myself a little bit more space to write. You do not need a ton of space to write. You don't got to forget about that. I just cut them apart and put them on there so that you could have that and not have to worry about speed writing these down. We could just think it. I have that for several of the questions we're going to do over the next few days, trying to make sure we can get through everything we need to get through before break. So, we're looking at kind of our basicest of most basic forms, the same one we used for our fruit flies question. So we're thinking about our a times b to the x. That's all the pieces we have over here. So we need to check and see, first of all, is a positive, and then is b bigger than 0 or small, or bigger than 1 or smaller than 1? To see if it is growth or if it is decay. So, on this first one, y equals 2 to the x. What do we think? Growth or decay? Growth. Why? Yeah. Our a is a positive 1. Our base is 2. 2 is bigger than 1, and 1 is also positive. So this is growth. Our base is 2. On the second one, what's our base? 1/3. So our b is 1/3. So what is this? Growth or decay? Decay. It's going to get slightly harder as we go through things. On our next one, the y equals 2 times 3 to the x. What do we think? growth. I've got a positive a value and a big base. So we've got 3 as our base. So this is growth. Second row, slightly harder. What do we think? Yeah, my a is a positive 5. Totally fine. My base is 1/5. 1/5 is smaller than 1, so this is decay. Last two are be careful mode.
But didn't you say all the A's are positive?
No, our a's have the same job as they had before, so it can reflect.
So is this B that's negative? But won't you multiply?
B cannot be negative,
But A. Okay.
but a can be negative. A still does our same job. It'll have that reflection across the x-axis.
So, oh wait, so this is like,
So we have a negative a value,
which is reflection.
which means it was reflected. So if I just had 2 to the x, that would be growth. Absolutely. 2 to the x would look like this, is growth. If it's reflected across the x-axis, it's gonna look like this. This means it's been reflected, because our a value does the same things it's always done for transformations. Since it's being reflected across our x-axis, now it is decay. So be super careful for those a values. Our next one is tricky in a different way. We've got y equals 7 to the minus x. We didn't have minus x's in our thing. We don't have minus x's in our formula.
Would it be 1/7?
Yes.
Oh.
Pulling out some old school exponent rules. I was going to rewrite this as 7 to the power of -1 to the x, because -1 times x is the same thing as minus x. 7 to the power of -1, that's 1/7. This is the same thing as 1/7 to the x. So this is decay. So old school exponent laws are going to come back into play.
So anything with a negative exponent is decay?
No, anything with a negative exponent, we're going to flip what's inside, because it could be minus, or like 1/3 to the minus x, which would then flip that to be a 3 to the x. So anything that's a negative exponent will flip our base.
So as long as it's been reflected, it's decay.
If it's been reflected, it's going to be opposite of what we think the base is. So it switches our base rule. So if it was minus 1/3 to the x, that would have been decay that reflected. So if it was, looking at you, there you go, decay, this way. And it reflects, it's starting super low, and it's growing. Okay, so weird, awkward, still gotta rewrap our brain around it. This is one of those pieces that helps us get our brain back into that exponential mode. Before we go back into some more algebra 2 stuff. We've done, I promise we've done it. Because what we're gonna do is we're gonna take these exponential functions and we're gonna play with them. We're not gonna graph today, but we're gonna look at some solving stuff.
Oh.
These ones I didn't print for us because we need to have space and we're gonna write. So solving these pieces, our exponential functions, when we're solving, we're going to be given 2 expressions. And what we want to do is we want to either have them be or get them to be the same base. We need to have the same base so that we can look at our exponents on their own. So our goal is going to get to the same base so that I can set my exponents equal to each other. Because if I have 2 to the x that's equal to 2/3, I would know that that x has to be 3, because for 2 to the x to be the same as 2/3, those things have to be the same. So if I have 5 to the 2x plus 11 and 5 to the 2 minus x, I know these 2 statements in my exponents have to be the same. In order for 5 to the something to be the exact same thing as 5 to a different thing, those two pieces must be identical. So this guy has to equal this guy. Since my bases are the same, I don't have to do any work to get there, which we like. So all I need to do is to take the fact that my 2x plus 11 has to equal 2 minus x. We're looking at our exponents because we need them to have the same base in order for those exponents to be exactly the same. What could I do to solve this?
Add x.
Mm-hmm. So if we add x to both sides, that's going to give me 3x plus 11 equals 2. Subtract 11 from both sides. I'm just going to take a no step first. So we're going to have our 3x equals negative 9. So what does x equal? X equals negative 3. You can to check it. You don't have to. Our 2 times negative 3 would be negative 6 plus 11. So we'd wind up with 5 to the 5th. And 2 minus negative 3, 2 plus 3, so 5 to the 5th. So we wind up with 5 to the 5th equals 5 to the 5th, which is in fact true. So that's how you could check it if you're not super confident in it. Let's look at the right-hand one. The right-hand one didn't come with same bases pre-installed. So what could we do?
Square it.
We don't want to square it, but I want to rewrite one of these.
Oh, good. No, I don't know.
9 is also known as
3 squared.
3 squared. So I could rewrite this 9 as 3 squared.
Wait, so you, and then so is it possible that you could square the 3 instead? Or would that be harder?
That would be harder, because then you're going to have to square the whole, it'd be a whole lot of.
Oh, no, never mind.
Go for your same bases. That's going to be less annoying.
Okay.
So I can rewrite 9 as 3 squared, and we kind of touched on this in the last one on the is it growth or decay. If I have a power raised to a power, what do I do with those two values? Multiply them. So this is the same thing as, I'm just going to skip lines, so I have a little more space. 3 to the 5x minus 8, and 3 to the 2 times x plus 2. Now I have the same base, so now I can just look at my exponents. I can just look at my 5x minus 8 and my 2 times x plus 2. So I want to know, when does 5x minus 8 equal my 2x, or my 2 times x plus 2? I'm going to distribute that out. My 2x plus 4. So we get our bases to be the same, and then we wind up with significantly easier problems. Because what do I do here to solve this? Minus 2x.
Add 4. I mean 8.
Yeah, so we can minus 2x from both sides to get to our 3x minus 8 equals 4. And then I heard it on the last one, we're going to add 8 to both sides so that we then get our 3x equals 12. And then we divide both sides by 3, and we get our x equals 4. So get yourself to the same base, and then we can do what we need to here. Okay, we're doing that. Questions on these two? Okay. A few more of these. So I've got 9 to the 2x equals 27 to the x minus 1. What are we going to do here?
Shrinking down to 3 to
Yeah. 27 isn't a power of 9. It's a multiple of 9, but not a power of 9. So we can't use a common base of 9. However, they're both powers of 3. So we can change both bases. That's fine. We may have to do that. So I can rewrite my 9 as 3 squared to the power of 2x. And I can rewrite my 27 as 3 cubed to the power of x minus 1. So we may have to change both bases to get to the same base, and that's okay. So what are we going to get for our statements to set equal to each other? What are we going to do next?
Multiply the 2 into x.
Mm-hmm. Yeah, we can do that multiplication. What are we going to get? 4x.
Equals 3x minus
3x minus 3. We multiply our powers together when we have a power raised to a power. What do we do?
Subtract 2x.
Minus 3x, and we're going to get
X equals 3.
x equals negative 3. Right one is very similar. What base are we going to change the right one to?
2.
To 2's. I can write 4 as 2 squared to the power of 2x minus 1. And we can write 8 as what? 2 to the third. 2 to the third. To the x. So what are my two statements that we're going to set equal to each other?
4x minus 2 equals
4x minus 2 equals 3x.
It's 4 minus 2.
Sure is. Oh, I love that. I wrote down the problem out of my notes. That's fun. Let's do it the first time I show. What do we do next?
Oh, so subtract 4x.
We can do that. Totally fine. Minus 4x. To get our x's together. So we get that minus 2 equals minus x. So what does x equal? 2. Okay. Hopefully vaguely familiar. We've done some definitely like this before. May or may not have done ones like this before.
Can do 2. Wait.
Huh? So we've got 4 to the power of x squared plus 8 equals 64 to the power of 2x. Does not change what we do. Same basis is our first goal. What's up? Precious, where'd I lose you?
Sorry, I was just like I was confused if like the x was going up with the 8 or the 2, but I think it's not going to be
It's 4 to the power of x squared plus 8 unit. Those are all in the exponent, x squared plus 8 equals 64 to the power of 2x. So, same goal, same base. How could I write this with the same base? Which of these? 64 is the same thing as 4 cubed. So I can write this as 4 cubed to the power of 2x. And the left side staying the same right now, 4 to the x squared plus 8. So again, we're going to multiply our exponents when we have a power raised over a power over here. So I'm just going to write down here. So we have our 4 to the x squared plus 8 equals 4 to the power of 6x. My bases are the same. So I just look at my exponents now. And I want to know when does x squared plus 8 equal 6x. So we're going to write down when does x squared plus 8 equal 6x. It's a quadratic. What do we do to solve a quadratic? What do I got to do before I can factor it? Set it equal to 0. So we're going to subtract our 6x from both sides to get x squared minus 6x plus 8 equals 0. What can we do here? This one factors nicely. X is in the front. Multiplies to make 8. Adds to make negative 6. Negative 4 and negative 2. So our solutions, plural, x equals 4 and x equals 2. Both of those will make those two statements be the same. So we can do this. We've done these before. Like, we can solve these kinds of equations. They're not brutally awful. We've seen this before. One more. We'll do the one on the right, and that's the last one. Same kind of vibe. What do I need to do on the right-hand one? We're going to make the 25 into a 5 squared. So this guy's going to be 5 squared to the power of x squared. And this side is 5 to the x plus 6. Yes. So what are my two statements going to be when I set my exponents equal? 2x squared equals x plus 6. So what do I do to solve this? Set it equal to 0. 2x squared minus x minus 6 equals 0. Will this factor? Yes. Factor using whatever method you choose. What are we going to get as our factors? Say it louder. There we go. Watch out for that a value because we're going to have our 2x plus 3 and our x minus 2. Most of us caught that this is going to split into our minus 4x and our plus 3x. Make sure when you're factoring, we pay attention to that. So this needs to be our minus 4x plus 3x minus 6. You can do it factoring by grouping, totally fine. Break it into our pairs, pull our GCFs, do it that way. You can put it through the box, whatever method you choose. But when we have an a value, slow down. What are our solutions going to be? X equals 2 and x equals negative 3 halves. Okay? What's up? Oh, this guy here. That's from when we multiply to make, we multiply to make negative 12 and add to make negative 1. This guy, minus 4, positive 3. That's how this middle term splits into our two pieces here.
I did the wrong thing.
There are many options for factoring. If you wound up with the right factors, you probably did okay. If we did not get quite to the right factors, go back and double check your factoring. So I put up here the 5.2 numbers. We have not gotten quite all the way into 5.3. We still have a little bit left to go in 5.2. Why are you trying to spell pants?